So the three kinematics equations that we're going to use, I wrote them up here last time. The three kinematics equations that we're going to use over and over again, and these only hold for constant acceleration. Remember that in order to make sense out of these, P initial and V initial have to be the position and velocity when time is equal to 0. And P final and V final have to be the position and velocity when time is equal to time final. And then the three equations are V final is equal to V initial plus A T final. The second one is P final is equal to P initial plus V initial times time final plus 1/2 A TF squared. And then the last one is 2A times the quantity PF minus PI is equal to VF squared minus VI squared. Okay, those are the three. And somebody asked me last time, like, oh, well, what's different about them, or what do they all do? Like, really, you can think of them all as the same. They're all just relationships between the variables defined here and the acceleration. They just all have different combinations of variables. So, like, for example, if you need to solve for the acceleration, and the only things you know are V final, V initial, and time final, then this is the one you would use. You know. On the other hand, if you didn't know V final, but you knew T final, V initial, P initial, and P final, you could use the second one to calculate the acceleration. So which one you use just depends on what variables you have, what you know. So let me go into a list of steps for how to use this, and then I'm just going to do example problems for a while. So this is a general set of steps for using the kinematics equations. And we're still doing kinematics along a line. We'll see that we have sort of very similar equations when we go to 2D and 3D. Okay, so the first thing you have to do is, well, what was the thing we had to do in order to, we had to specify some stuff before we could, yeah, before we could plot the position versus time graph. What were the things we had to specify? Do you remember? Yep.
Is constant acceleration one of them?
That's required for these, but that's the things I'm thinking of. Yeah, so you had to, the three I'm thinking of are, you had to choose a location that you're going to call position equals 0. You have to choose a direction that you're going to call positive, and then that also means that the opposite direction is negative. And you have to choose an instant that corresponds to time equals 0. So basically that's what you have to choose here, except you also have to choose an instant to correspond to time final. So the first step is to specify a location corresponding to P equals 0. In other words, you're saying, so if you're measuring the motion of a car going down the street, you're saying this point on the street is what I'm going to call my 0 position. You can think of that as like I'm setting my ruler down at this point in the street. Okay. You also have to specify a direction corresponding to positive. I'll call it positive position. You have to specify an instant in time corresponding to time equals 0. So if the car is going by on the street, you're saying, okay, right now I'm turning on the stopwatch. Okay, that's the instant time is equal to 0. And you also have to choose an instant corresponding to time final, which you can think of as, you can think of this one as stopwatch going on, and this one as stopwatch going off. Okay, so that's the first step, specifying those 4 things. The second step is list out all the variables that you know and the variables that you want. One thing, just to go back to this for a second. How do you choose these 2 instants? How do you choose when to turn the stopwatch on and off? You want to choose instants where you know stuff and where you want to know stuff. Okay, like if you're timing someone doing the 100-meter dash, you start it when they're at the beginning. You know that they've gone 0 meters. And you stop it when you know they've gone 100 meters. If you choose to start it when they're in the car driving to the track and stop it halfway through the race, that doesn't tell you anything about how fast they run 100 meters. Okay? So you choose these based on when you know stuff and when you want stuff. Okay, so the variables that you know and the variables you want, for example, once you've specified these 4 things, you might know, I usually write it out in 2 columns like this. So here's the stuff I know, here's the stuff I want. We might know the acceleration, the initial velocity, that's the velocity when time is equal to 0, the final position, and the position when time is equal to 0. And we want to calculate the velocity when time is equal to time final. Okay. Then step 3. Based on what you know and what you want, choose an equation that contains the variable you want and every other variable is known. That's because you can, one equation can let you solve for one variable. So every other variable is known. So in this example, see if this is solvable. Which one of those three equations has VF in it? Well, I didn't even ask the question yet. So yeah, which one has VF in it, and then everything else in it is known? I think the third one. And the thing about the first and the second one is they both have time in them. The third one is the only one that doesn't have time. But so you can use 2 times A times the quantity P final minus P initial is equal to VF squared minus VI squared. Because V final is in it, A is in it, VI is in it, PF is in it, PI is in it. All right, and actually, I said that a little bit backwards. So VF has to be in it, but really the question is, now go through all the other variables in this equation. Do they appear in the known column? Okay, so yeah, A you know, PF you know, PI you know, VI you know, so this is the one we want. Sometimes that's not enough. More than half the time that you do these problems, that will be, but so step star. If no equation works, find an equation that lets you solve for an intermediate variable and these intermediate variables will usually be TF or A, and then go back to step 2. So the idea there is, if you look at what you know and what you want, none of those three equations work, then try solving for A or try solving for TF, list them out again, and then see if, now that you know one more bit of information, is there an equation that lets you solve for what you want? So just do it in 2 steps sometimes. Okay, so here's the first example. Let's say a car is going at 50 miles per hour. And hits the brakes. We're going to assume that the acceleration is constant. So let's say that the car stops over a distance of 30 meters. So it requires 30 meters to stop. What's the acceleration? This is how to draw a car that's stopping. Make the wheels go backwards. If you draw children's books. Like in Go Dog Go, this is how they do it. And so the distance that it takes to stop is 30 meters. All right, so the first thing we're going to do is specify those 4. The position equals 0, the positive direction, the time equals 0, and the time final. as far as choosing these things, choosing the position equals 0 and the positive direction are always arbitrary. There are ways you can do it so it's a little easier sometimes and a little harder sometimes, but it'll always work with anything. Choosing the right time equals 0 and time final is necessary to do the problem. If you choose the wrong times, you can't do the problem. Okay. The other two you have a little more flexibility with. But okay, so what do you want to choose as position equals 0? There's probably two sensible choices that'll make the math easiest. One is position equals 0 right when the car starts to brake, and the other one is position equals 0 when the car reaches rest, comes to rest. Let's choose when it starts, like when it first puts on the brakes. So let's say P equals 0 is the car's location when it hits the brakes. So that's saying where we're going to set the ruler down on the street. And then positive direction, again, that's arbitrary. All things being equal, I suppose people usually put it in the direction of motion. So positive direction, we'll make that the direction of the car's motion. Okay, so now these are the two that we need to get right. There's a right and a wrong, and we need to get them right. So we have to think of the instance where we know information and where we want to find information. Then t equals 0 is always the earlier one, and t final is always the later one. So what are the two instances where we know stuff? Yeah, so we'll call time equals 0 the instant that the car hits the brakes. And time final is when the car has traveled 30 meters. I'll say for now that the car reaches rest. And now based on these choices, we can define all of those. Well, we won't know what they all are, but now those variables, the initial position, initial velocity, final position, final velocity, acceleration, those are all defined. So let's think about which one of those we can come up with values for and which ones we can't. Well, I'm going to just go through them in order. I'm going to think, so if you list all the possible variables that you could know, that's T final, A, P initial, P final, V initial, and V final. So I'm just going to go through that list and figure out which ones we know and which ones we don't. Do we know time final? Do we know how long after the car hits the brakes? Nope, we don't. We're not given any information about the elapsed time. Are we asked for that? No, so we don't know it, but we don't want it either. So if we can get by without ever learning it, that'd be fine with us. Okay, so I'm going to leave that off. What about acceleration? Do we know that? No? Do we want it? Yeah, that's what we're asked for. What about P initial? Do we know, so remember what P initial means. So do we know the position of the car at the instant that time is equal to 0? Yep. So PI is equal to 0 because we put our 0 position at the place where the car is when time is equal to 0, remember? Time is equal to 0 when the car starts to brake. And we put our position equals 0 where the car is when it starts to brake. Okay. Do we know the final position? When the car reaches rest, do we know its position given our positive direction and our 0 position? Yeah, we know that that it's gone 30 meters in the positive direction from our 0. So P final is equal to positive 30 meters. I'll put a positive here just so you remember that can be plus or minus. In this case, it's positive. Yes?
Would it be wrong to say that P final is equal to PI plus 30 meters? Would that be wrong?
That's right. That would just make the equations a little messier, but you could do it like that. Okay, what about velocity when time is equal to 0? Do we know anything about that? Right at the instant that it starts to brake. We're given that speed is 50 meters per second. Not 50 meters per second, actually, 50 miles per hour. So we have to convert that. So VI is equal to 50 miles per hour. And if you go through the conversion, 1 mile is 1609.344 meters. And 1 hour is 3,600 seconds. So when you convert to meters per second, you get 22.35 meters per second. And then the last one, we've gone through all of the list except V final. Do we know what the velocity of the car is when time is equal to TF? 0. It comes to rest, so speed is 0, the velocity is 0. So VF is equal to 0. Okay, is there an equation that has acceleration in it and every other variable in it shows up in this list? Yep. So this one works. 2a times the quantity PF minus PI is equal to VF squared minus VI squared. And I'm going to use all of the units in this calculation. So we have 2 times, and I'm going to write it out in that numerator denominator notation that I've been using for unit conversion. So we have 2 times. Then the acceleration is, well, we're trying to find that. Then we have the quantity PF minus P0. So that's 30 meters minus 0. And that's equal to VF squared. So VF is equal to 0. How am I going to write this? 0 meters per second times 0 meters per second. And then minus V initial squared. So 22.35 meters per second times 22.35 meters per second. So this block, we get 2 times A times 30 meters gives 60 meters times A. And that's equal to 0 minus 22.35 squared. So that's negative 499.52 meters squared per second squared. And now I want to get A by itself, so I'm going to divide both sides by 60 meters. Yes? No. So divide both sides by 60 meters, and you get that A is equal to, I'm going to use that unit conversion formatting again, so negative 499.52 meters times meters over seconds times seconds. And now I'm going to divide by 60 meters. That meter cancels one of those. And our final answer, yep. And don't forget the negative. Those signs are important. So negative 8.33 meters per second squared. So notice, if you do it right, the units will always work out. We got meters per second squared, which is the SI units for acceleration. And then what about the negative sign on the acceleration? Is there any way we can think about that that'll tell us whether that makes sense or not? So it does make sense that it's negative. Be sure that you don't think of it as, so remember last time I said something speeding up if the sign of the velocity and acceleration are the same, and it's slowing down if the sign of the velocity and acceleration are opposite. So in this case, this is consistent with it slowing down because the velocity, it's originally moving in the positive direction. The positive direction is this way. So the velocity is positive. And so velocity and acceleration are opposite signs. It's slowing down. Any other questions about that one? Okay, here's another one. So let's say this is one of those circus cannons. So there's a platform and a spring, and the human cannonball's inside waiting to launch. With arms, and they light the wick, but that's just for show. You guys might not have known that, but there's not actually an explosion in there. Okay. Well, you're smarter than you look. So let's say that the length of this cannon is 3 meters long. And so this platform is gonna launch the astronaut from here. It's gonna extend until it gets all the way to the end. And over that distance of 3 meters, did I say astronaut? That's that's bad news if he ends up as an astronaut from this thing. That's not going to finish well. The human cannonball over 3 meters goes from rest to 12 meters per second. And we want to calculate two things. First, what's the acceleration? What's the acceleration over the 3 meters? And second, how long does it take to cover those 3 meters? To travel those 3 meters. Well, I'm going to go through the whole process for A, and then we'll go back and do B. So the first step is we have to specify those 4 things. What do we want to choose as our position equals 0? Again, this is just a matter of, this is arbitrary. You can choose what you want. But I think most people would probably choose the same thing. Let's say we'll choose, and actually, let me do it in another order. Let me do the important ones first, and then I think it can sort of help clarify how to think about this. So these are the two that you don't have any wiggle room on. You have to get these right. What's the instant when time is equal to 0? Yeah, so right at the instant that he starts to move. And what do we want to choose as our instant time final? So we want a time final to happen when he's traveled 3 meters. We want it to be at that instant right when he's made it to 3 meters. And now we can choose the 2 position ones. So position equals 0. Let's choose the human cannonball's position when time is equal to 0. Okay, that's what we did in the last one. I didn't word it that way, but I think that's a nice way to think about it. So this is the person's position when time is equal to 0. And whenever your position equals 0 corresponds to the position when time is equal to 0, what you're doing is you're specifying that PI is equal to 0. Because PI is defined as the position when time is equal to 0. So basically we're saying, this is another wording of saying, make PI equal to 0. And then the positive direction, you could do this however you want, but let's put it in the direction of motion. Okay, now let's list out what we know and what we want. So TF, do we know the elapsed time for the motion? No? Do we want it? We want it for part B, but we don't want it yet. So I'm just going to leave it off. What about A? We want that. We don't know it. What about PI? We know that the way we specified our position equals 0 required that PI is equal to 0. What about P final? We know that P final is 3 meters in the positive direction from the 0 position. And so P final has to be positive 3 meters. What about V initial, the velocity when time is equal to 0? That is 0, yep. He doesn't start, he's at rest, and he doesn't start moving until after, time equals 0 is when it all starts. So VI is equal to 0. And then at time final, what's the velocity? And is it positive or negative? So the speed is definitely 12 meters per second. It's positive because he's moving in what we defined as the positive direction. Is there an equation that works with those? I think it's the same one again. Anytime you don't have time final appearing, that third equation is the only possibility. So 2 times A times P final minus P initial is equal to V final squared minus V initial squared. That's just 0 squared. And if you multiply these out, you get 6 meters times A is equal to, you have to square everything in here, so 144 meters squared per second squared. And now to get A by itself, we're going to divide by 6 meters. So A is equal to 144. All right, it is 144 meters times meters over seconds times seconds. And then I'm going to divide it by 6 meters. The meters cancel one of those. And you get an acceleration of 24 meters per second squared. And it came out positive. Does the positive make sense? How do you know that makes sense? The velocity is positive. He's moving in the positive direction. He's speeding up, so the acceleration has to be the same direction as the velocity. Okay. Is that survivable? 24 meters per second squared? Like, is that comfortable, or it squish you flat, or? Yeah, that's a pretty high acceleration, but it's not too, like, fighter pilots deal with G forces much bigger than that. If the acceleration of gravity in free fall is about 9.8 meters per second squared, so this is about 2.5 Gs. And so, yeah, that's fine. There would be a bigger acceleration if he was decelerated by hitting the ground at the end of that, and that would be more of an issue, but this would be fine. This part is fine. They usually have some kind of net, though, or something. Okay, so now the second part, we want to figure out the elapsed time. So I'm going to go through all those steps again. So with those things that we specify, is there any reason to change any of those?
Yes. And then acceleration, and we want the final.
That's exactly right. That's not the step we're on yet, but yes, that's exactly what we're going to change. So the step here is just like choosing what's t equals 0, t equals t final, that kind of stuff. There's no reason to change any of that. So we'll just keep all this the same. And if you keep these all the same, then all the numbers that you used in the previous example still hold. You know, your 0 is still in the same place. Your positive direction still means the same thing. So let's list out what we know and what we want. Do we know time final? No, but we want it. That's what we're asking for in part B. Do we know acceleration? Yeah, this time we do. So A is equal to positive 24 meters per second squared. Do we know P initial? Well, all the rest of it is going to be just like it was. So when time is equal to 0, the position is 0. PF, when time is t final, the position is positive 3 meters. V initial, 0, and V final, positive 12. And is there an equation that has TF in it and then everything else in it appears here? Yeah, the first one. So we can use the equation that says V final is equal to V initial plus A TF. So 12 meters per second is equal to 0 plus the quantity 24 meters per second squared times TF. I'm going to divide both sides by 24 meters per second squared. So when I divide the left by 24 meters per second squared, we get 12 meters over seconds divided by 24 meters with seconds times seconds in the numerator. Anybody want to look at that for a second and express disbelief or frustration? So since I divided by 24 meters per second squared, everything got switched from numerator to denominator and vice versa. So the meters cancel. One of the seconds cancels. And we get TF is equal to 0.5 seconds. Yes. Yep, I'll always give you those. Bless you. Yes?
I'm sorry, why did you flip it?
I divided, so dividing just flips everything. Let me, yeah, I'll give you some problems to work on together after I finish this, but let me talk about free fall first. So free fall and projectile motion is the most important example of constant acceleration kinematics. These two terms are interchangeable, even though They sound pretty different. But in either case, all that it's saying is the only force acting on the object is weight, is gravity. So the only force acting on the object is gravity. So how often does that happen, that the only force acting is gravity? Well, never, on Earth, never. And so we're going to use this a lot. So it's important to remember that this is an approximation, and the question is, how good an approximation is it for the event that we're dealing with? So that never actually occurs. So when is it a reasonable approximation? So there's two things that matter, sort of two requirements for using this approximation. The first one is that nothing's touching the boundary of the object. So like, for example, this pen, we know we're not going to treat this like it's in free fall because it's sitting on the table. The table's touching it. So that's easy. And then the second thing is the force of air resistance is small compared to the force of gravity. Air resistance affects the motion much less than gravity does. Okay, so the first one of those two requirements is easy to verify. The second one is, that's always an issue, and it has to do with how accurate you expect your results to be and stuff like that. But I can give some sort of guidelines for thinking about that. So this is the big one. So what determines the size of the air resistance effect, let's say? What determines how much air resistance affects the motion? Well, there are a few things, three things. The first one is the mass of the object. If everything else about the object stays the same, the more massive an object is, the less air resistance affects its motion. So if you increase the mass, that causes a decrease in the air resistance effect. So for an example, let's say that So imagine you had like a beach ball this big, okay? And then imagine you had a ball that was the exact same size and shape, but it was made out of steel. You know, it would be like 2,000. It wouldn't be that much. It would be probably close to 1,000 pounds. Okay, it would be super, super heavy. And then you drop the two of them off the roof of a house or something. You know, which one is going to be affected by gravity more? Well, the beach ball, we know from experience, is going to blow all over the place from the wind and whatever. It's affected by air resistance a lot. The steel ball isn't going to be affected at all. You know, so mass is the first thing that determines. The second thing is the surface area. If you decrease the surface area, it makes the effect of air resistance get smaller. Reduces the air resistance effect. An example of that, say that you had an army man hooked up to a parachute, you know, and however much that weighs, maybe that weighs 200 grams or something, and imagine a ball or a rock that weighs the same amount, you know. Which is going to be more affected by air resistance when you drop them? The army man with a parachute or the rock? The parachute is designed to pick up a lot of air resistance by having a giant surface area, and so it's going to flutter down to the ground really slowly while the rock basically falls like it's in free fall. Okay, so that's the surface area. That's what surface area does. And then the last one is speed. So if the speed is lower, then there's a reduced air resistance effect. And so even the same object, it's not a question of whether an object can be treated like it's in free fall. It depends on what kind of motion it's in. If it's going slowly through the air, then it can be modeled as free fall much more accurately than if it's going fast. So, for example, a baseball, if I held a baseball like this and dropped it down to the table, assuming that it was in free fall would be a nearly perfect approximation, you know. But a baseball, if someone hits a baseball 400 feet, and as it leaves the bat it's going 120 miles an hour or something, you'd get really bad approximations, really bad results by assuming that it was in projectile motion or free fall because it's going so fast, even though it's the same object. The speed thing, yeah, well, have you ever noticed, like, I don't know, probably not. When I did this example, everybody used to like to watch bike racing because Lance Armstrong was good and not the world's biggest cheater yet or whatever. Well, he was, but we didn't know it. I still like Lance Armstrong, but anyways, they do the Tour de France, you know, like almost the whole race, they ride in a big pack together, you know, just to reduce the air resistance effect. And if someone tries to take off, everyone just goes and catches, and then they huddle up together. And there's only a couple of kinds of races where you have a chance to gain time on people. And the biggest one is the time trials, where they don't let people ride together. You have to do it by yourself. And they do these time trials in two ways. They do ones that are on the flat, and they do ones where they go up through the Alps. And if you see them on the ones where they're on the flat, they're wearing these like space-age suits, all rubberized. They're wearing the helmets with the teardrops. Their arms are like this. Everything that they've done, they've even like the cables that shift the gears and stuff, they've been real careful to run those inside the bicycle and stuff. They've done everything possible to reduce air resistance. And then you watch the time trials, which are equally important, where they're going up the mountains. And they're just using regular-looking bikes. They're not using the funny-looking bikes. They're not wearing the funny helmets. They're not wearing the rubber stuff. Their shirts are unbuttoned so they don't overheat. They have their hands up on the top like they're just like riding a Huffy or whatever. And so, like, what's the difference? The difference is that when they're on the flat, they're going 40 miles an hour. And when they're going up the mountains, they're going 15 miles an hour. And that difference is enough that air resistance is almost the only thing that matters on the flat, and it's virtually irrelevant going up the mountains. So it's just the speed thing. And so if you can assume, if you make the free fall assumption, then the acceleration of an object in free fall is always the same no matter what it's doing. Is always the same. (9.81 meters per second squared down). That's on Earth, but that's all our problems are gonna assume we're on, near the surface of the Earth. Okay, so I said projectile motion and free fall are the same thing. So what about like projectile motion when I throw this object up into the air? For half of its motion, it's going up. So what about the fact that the acceleration, I said, is 9.81 meters per second squared down no matter what if it's in free fall? What about when it's going up? Yep. Yeah, so that's right. So when it's going up, the velocity is positive until it gets to the top of its path. But the acceleration, even when it's going up, is down at 9.81 meters per second squared. And then it gets to the top and starts coming down, and then its velocity is down, and its acceleration is still down. And you can make sense out of that if you think of what it's doing. Like let me try that again. On the way up, it's slowing down until it gets to the highest point, and on the way down, it's speeding up. Okay? It's hard to see in that little distance, but it starts out with a speed going up, slows down until it stops at the top, and then it starts speeding up going down. And so when it's on the way up, its velocity is up. It's slowing down. That means its acceleration has to be the opposite direction of the velocity. Okay? And so when it's on the way up, since it's slowing down, you know the acceleration is down. And then when it gets to the top and starts coming down, it's speeding up. Its velocity is down. So that means the acceleration has to be down then too. And so you're going to, most likely, everyone in here is going to make this mistake a couple times at least. But try to remind yourself that the motion doesn't have any effect on the acceleration. The acceleration is 9.81 meters per second squared down. That just comes from gravity anytime an object is in projectile motion or free fall. Okay? I want to show a video. Let's see if I can find it. So I think it's a little hard for people to accept a lot of times that without air resistance, everything falling would accelerate exactly the same, like a feather, a parachute, a helicopter, a steel ball. They would all accelerate down at 9.81 meters per second squared if there was no air resistance. It's a little hard to imagine because it's so far, getting rid of air resistance is so far outside of our experience. But let me see if I can find this video. What is Burning Man like? Should we watch that instead? I've always been curious. Let's see. Okay. So this is the world's largest vacuum chamber. I wonder if I have a sound thing here.
This is NASA's
And so-
power facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear.
I guess let me just do it on the other computer and then you can listen to it. But basically the idea of this is that they are going to. So here are two things that are going to come up really often in free fall problems. Two common strategies for free fall problems. And I'm going to just keep calling them free fall problems, but remember I'm also talking about projectile motion problems when I say that. The first one is if an object is launched up into the air, at the highest point in its flight, its velocity is equal to 0. So if we're trying to figure out how high something goes before it starts falling back down, we can specify that we know that the velocity is equal to 0 at that instant and use that to solve for other stuff. And then the second strategy that we're going to use is if an object is dropped, then at that instant, it has the same velocity as what it was dropped from, the vehicle or whatever. It has the same velocity as what it's dropped from. So if you're in an elevator that's moving up at 2 meters per second and you drop something, at the instant you drop it, it's moving 2 meters per second up. And if you're in a helicopter, and you drop something out the window, at that first instant, its velocity is whatever the velocity of the helicopter is. if you're on something that doesn't move, a bridge or whatever, and you drop something, the bridge's velocity is 0, so the object's velocity is 0 when you drop it. Okay, let me just do a simple problem. So let's say an object is dropped from a height of 3 meters. How long does it take for it to hit the ground? Okay, so the object's dropped from 3 meters above the ground. The first thing we have to do is specify those 4 things. So time equals 0 is going to be when it's dropped. Time final is going to be when it hits the ground. P equals 0 is, let's make that the ground. That's arbitrary, but let's make that the ground. And then positive direction, I'm going to make that up. And I would recommend always doing that in free fall problems. Okay, so now we have to figure out what we know and what we want. Do we know time final? We do. We want to come up with a number for that. So that's what we're looking for. Do we know the acceleration? It's free fall, so in free fall problems we always know that. It's 9.81 meters per second squared down. If up is positive, then A is negative 9.81 meters per second squared. Do we know P initial, the position when time is equal to 0? If our 0 is here and our positive is that way, then when time is equal to 0, the position is 3. And when t is time final, the final position is 0, because that's when it hits the ground. When time is equal to 0, what's the velocity equal to? That's the acceleration. When it's released, it's being dropped from something that's not moving at all, so this is just equal to 0. And then when it hits the ground, we don't know anything about the velocity, but we don't care, so we'll leave that off. The equation that works here is P final is equal to P initial plus V initial times T final plus 1/2 A T final squared. And so you get 3 meters is equal to, oh no, I did it backwards. P final is 0. So 0 is equal to 3 meters plus 0 plus 1/2 times negative 9.81 meters per second squared times TF squared. So you get negative 3 meters is equal to negative 4.905 meters per second squared T final squared. You can cancel those negatives. And now divide both sides by 4.905 meters per second squared. So 3 meters divided by 4.905 meters with seconds times seconds on top. Does anyone have a calculator? Can you divide 3 meters divided by 4.905? 0.612. The meters cancel. So this is seconds squared. And that's equal to T final squared. So now take the square root of that. And T final is equal to plus or minus. What's the square root of 0.612? 0.782 seconds. That's two answers. We want 1 second. So do we want the positive or negative 0.782? We want positive because we don't deal with negative times. So the answer is positive 0.782 seconds. Any questions about that? Okay.